Come to the problem 5, the test 3 extras. Problem 5, it says a helium gas balloon occupying a volume of 2 liters starts out at the surface of the earth at 20 degrees Celsius. So here you have the balloon at 20 degrees Celsius, helium gas balloon, and then you let go of the balloon. Of course it rises. As it rises, what happens to the temperature of the air? The temperature of the air cools down, right? So it says it rises until the temperature drops to -50 Celsius. What is the initial and final pressure in the balloon in atmospheres and pascals? Okay, so we're going to assume in this problem that the volume of the balloon is staying constant. In reality, that's probably not going to happen. So assume the volume stays constant. So it goes up. What's going to be the final pressure of the balloon here? So this is P final, P initial. So if this is constant volume, then we have PV equals nRT. So what they want us to know is, what is the initial and final pressure in the balloon? What is the initial pressure? What is the final pressure in atmospheres and both pascals? Okay. So how are we going to do it? Well, we're going to have to use the density of helium. The density of helium is going to be 0.179 kilogram per cubic meter. Okay, why are we going to have to use that? Well, because they give you the volume of the balloon, right? So in order to know how many moles of balloon, you're going to have to convert to the mass of the balloon, and you're going to then have to convert to using the molar mass of helium, convert to mass. Okay, the volume is equal to 2 liters. What's the conversion between a liter and a meter cubed? We know that 1,000 liters is 1 cubic meter, right? And then 1 cubic meter of the helium has a mass of 0.179 kilogram. Okay, and then of course 1 kilogram is 1,000 grams. I'm going to put it down here. 1 kilogram is 1,000 grams. Okay, and then what's the molar mass of helium? We know that 1 mole of helium has a mass of 4 grams because the atomic weight of helium is 4. Okay, so you look up a periodic table, you see that the atomic weight of helium is 4. 1 mole of helium is 4 grams. So 4 grams gives you 1 mole. So what happens here? When we do all of these conversions from liter to cubic meter to the mass, what are we getting here? The liters canceling the liter, the cubic meters canceling the cubic meter, kilogram canceling kilogram, gram canceling gram. We are actually calculating how many moles of material we actually have here. Divided by 4, that gives you the number of moles, 0.0895 moles. So in a typical helium balloon, occupying a volume of about 2 liters, so that's about something like this, right? Then you're going to have about 0.0895 moles. So we can put that in here now, okay? Okay, so now, what version of the R are we going to use? R is the gas constant. There's a couple different versions of the gas constant. There's one that says 8.31 joules per mole Kelvin, or 0.0821 or 0.0821, and that'll be liters atmospheres divided by mole Kelvin. So whenever we want to do in pascals, the pressure in pascals, whenever we want to express the volume in cubic meter, we use this version of the gas constant, 8.31. Whenever we want the volume to be expressed in liters and the pressure to be expressed in atmospheres, then we use this version. So in this problem, we can actually use either one since we are calculating the pressure of the balloon in both atmospheres and pascals. So we could say P, the volume, is equal to what? 2 liters, okay, for the volume, as was given here. The number of moles, 0.0895. Okay, the R is equal to 0.0821. So if this is liters, I should use the one that says liter atmosphere. Okay, what's the temperature? 20 degrees Celsius. You have to convert that to what? To Kelvin, right? So 20 plus 273.15. So when I calculate all of this, what is it going to give me? It's going to give me the pressure inside of the balloon in units of atmospheres. Okay? Of the helium gas is equal to 1.077 atmospheres. That actually makes kind of sense because you have to imagine when you're filling up the balloon, in order for the balloon to grow bigger and be tight, you need the pressure inside to be greater than the pressure outside, the pressure, atmospheric pressure, right? 1.077 atmospheres. As it goes up, what's going to happen? Both the air and the helium are going to cool down. The helium balloon's pressure is going to go down. The atmospheric pressure is going to go down. Well, depending on which one is greater, the balloon might get larger or the balloon might actually get smaller depending on if the air pressure is pushing in on the balloon, right? They're both going to go down. So how do I convert that to units of pascals? Well, 1 atmosphere, I've shown you this before too, 1 atmosphere is equal to what? 1.013 times 10 to the 5th Pascals, right? That's going to be 1.091 times 10 to the 5th Pascals. That's about 109,000 Pascals, you see? 109,100 Pascals. Whereas atmospheric pressure is 101,300 Pascals. So this one is 109,000, okay? Okay, so what would happen when we go up and the temperature goes down? Well, the only difference is that now we're going to have to put the new temperature here. So P times 2 is equal to 0.0895 and then 0.0821, negative 50 plus 273.15. Okay? And you can calculate the pressure again. Or what another way you could have done it is to say P2 over T2 is equal to P1 over T1. Because the volume is staying constant, the ratio of pressure to temperature is the same. So we don't necessarily have to go through these same calculations. We're assuming the number of moles stays the same also. So that means the ratio of the pressure to temperature is constant. So we have P2 divided by what? You have to make sure you convert to Kelvin. Negative 50 plus 273.15 is equal to the initial pressure, which was 1.077. 1.077 divided by 20 plus 273.15. Now, can you keep the units of the pressure in atmospheres, or does it have to be Pascal? The answer is that you can keep it in atmosphere or you can use the Pascal. Depending on which one you use, your final answer is going to be in that unit. But the Celsius, you do have to convert to Kelvin, because the ratio of the temperatures in Celsius is not the same as the ratio of the temperature in Kelvin. So it's because Celsius is not a true measure of temperature. It's just a scale that we have made so that 0 Celsius corresponds to the freezing point of water, 100 Celsius corresponds to the boiling point of water. So it's not really a true temperature scale. Okay, so now if we do this one, we're going to have what? It's going to be 1.077 times 293.15, and so the pressure inside of the balloon is equal to 0.82 atmospheres. Balloon's pressure has gone down, right? What's happened to the pressure of the air? The pressure of the air has gone down too, because there's less air there. The air is thinner. So depending on which one is weaker or stronger, the balloon might either go down or decrease in volume or increase in volume. Converting that to Pascals, we get the final pressure in Pascals. 0.82 atmosphere, multiply 1 atmosphere, 1.013 times 10 to the 5th. Atmospheres. So quite a lot less, right? Instead of 101,000, which is atmospheric pressure, it's only 83,000 atmospheres. So you can kind of see now how to do this kind of a calculation involving number of moles, the gas constant, the pressure changing, and all of that kind of stuff. Okay, thank you.